Hi guys, so in this video we're going to look at ordinary arithmetic on tensors as well as broadcasting, which is the set of rules PyTorch uses to combine tensors of different shapes. Broadcasting is convenient until the set of rules silently does something we didn't intend. We can start off by creating two 1D tensors with the same shape to work with. When two tensors are the same shape, the operators do exactly what we would expect position by position. Plus adds matching elements, minus subtracts them, and / divides them. Notably, using the star symbol, we do element-wise multiplication rather than matrix multiplication, which has its own operator. We can also define the exponent for each element using the double star operator. Every operator has an equivalent function. For instance, the mul function does element-wise multiplication. PyTorch also has a large library of these element-wise functions beyond the basic operators. When we combine a tensor with a plain Python number, it applies to every element. So tensor A plus 100 adds 100 to each of the three elements. Using an inequality gives a boolean for each element in the tensor. These results are not surprising, but somehow PyTorch has been able to combine a tensor with a plain Python number, and this is a simple example of broadcasting in PyTorch. Broadcasting also lets tensors of different shapes work together by expanding the smaller one to match the larger one without copying any memory. The rules compare the two shapes from right to left, dimension by dimension. If a pair of dimensions is already equal, fine, move on. If one of the pair is 1, stretch it to match the other dimension. Then if one tensor simply has fewer dimensions than the other, pretend it has extra 1s padded onto the left until the dimension counts match. And if none of that resolves a pair of tensors, it's an error. We can work through an example of seeing the rules applied. The tensor m has shape 3 by 4, and the tensor rho just has shape 4. Aligning from the right, the trailing 4s match, and as rho has no dimension left to compare against m's leading 3, it gets padded with a 1 on the left, making it effectively have a shape of 1 by 4. This 1 then gets stretched to match m's 3. The net effect is that rho gets added to every single row of m. We can also broadcast down the columns instead of across the rows. In this example, we can use the unsqueeze method to make the tensor the correct shape. Broadcasting also enables the stretching of multiple dimensions at once. This means that a 3 by 1 tensor can be combined with a 1 by 4 tensor to produce a 3 by 4 tensor. When intended, this is pretty elegant, however it can hide some errors. Finally, we have an example here where PyTorch raises an error. Comparing from the right, 4 and 3 are not equal, and neither is 1. So none of the rules apply, and PyTorch raises an error instead of guessing. The fix is to explicitly define the direction you want to broadcast. And so that's all for this video. Thanks for watching.